Hello, this is Dr. Berang Askarian. I am an associate professor at Washington State University, the Mechanical Engineering Department. I am also a licensed professional engineer in the state of Washington in the area of thermal fluids. This video is about external flow over a flat plate, a very classic subject in fluid mechanics. This video talks about the local friction coefficient and the significance of it and what it means. And the next video, I provide the link in the description, will talk about the average friction coefficient and how you can calculate the total drag force on a flat plate exposed to a parallel flow over it. And in the next video, we're going to categorize these problems into like at least 4 different categories, some approximate solutions, some exact solutions for laminar flow, turbulent flow. So first, we're going to talk about the idea of the critical Reynolds number and the local friction coefficient. Let's take a look at the flow over a flat plate first. So for this case, something that you are probably familiar with, that's why you looked up this video. If you have a flat plate like this, so this way, whoop, no, more time, there you go. So you have a flat plate and some fluid with the velocity of v is going over it. Let's say the density of the fluid is rho and the viscosity of this fluid is mu. It could be air over, like a fan, over a flat plate. What we know by now is that at the beginning of the plate, a boundary layer starts to form like this. And at some point, this boundary layer, if the flat plate is smooth, and this is just a smooth case, we're going to first start with talk with the smooth flat plate where epsilon is 0. At some point, which we call the critical x being measured from the beginning of the plate like this. Let's say this is our coordinate system, and this is how we measure our x. X equals 0 is here. At some point, Reynolds number, which this is the case, Reynolds X for an external flow over a flat plate is defined as density of the fluid times the free stream velocity of the fluid times x. X is the distance from the beginning of the plate over the density of over the viscosity of the fluid. If Reynolds number at this point, Reynolds X is less than 5 times 10 to the 5th, we call this flow laminar if the plate is smooth. If it's not smooth, that's not the case. It's going to be turbulent anyways. If Reynolds number is bigger than 5 times 10 to the 5th, then it is turbulent flow, like this. And why does it matter? Because for laminar flow and for turbulent flow, we have different equations, basically. So this is something that you're probably familiar with. Now, what's the idea of friction coefficient? Friction coefficient is the first they use the boundary layer solution using Navier-Stokes equations to find something called the friction coefficient. And what's the significance of friction coefficient? First, I'm going to introduce the significance of friction coefficient, local friction coefficient, and then how we can use that to find the total drag force. Let's take a look at that plate one more time. This is that plate. Let's say this is the width of that plate. And let's say this is x equals 0, and this is x equals L. So the length of this plate is basically L. And flow is going over it. That's that V, flow is going over it. Take a look at a strip on this plate, just a strip like this. This is a strip that has the length of dx. So this length is basically just dx. The distance from the beginning of the plate to this strip, this distance is obviously x. This distance is x. When we define the average, the local friction coefficient is supposed to give you the local shear stress. It is defined such that if you have the local friction coefficient and you multiply it by the the dynamic pressure caused by this flow over the plate, you can get the local shear stress at that point. And what does that mean? This is the local shear stress on this strip, on that strip, which will cause a local, very small amount of dF drag at point X, like this. That's dF point at X. If somebody wants to find the total drag force over the whole plate, basically you have to take the integral. The total drag force, F drag total on the plate, would be the integral of 0 to L dF dx. What is dF dx? dF dx is basically the local shear stress, x sub x times dA. In this particular case, for this problem, you can see that dA is just W times dx. So make sure that you understand this concept. You can pause the video, go back and rewatch this again, and make sure that you got this concept. So one more time, the local friction coefficient, it is defined such that if you multiply the local friction coefficient by the dynamic pressure, you get the local shear stress. If you multiply the local shear stress by the area of that strip, you get the dF drag. That's not the whole drag on the plate. That's just the dF drag. And why do we have just local? Why do we have just, an average, a total from the very beginning? The reason is the value of this local friction coefficient keeps changing with X. Not only that, it also keeps changing if the flow goes from laminar to turbulent. So it is a variable. It keeps changing. That's why you need to take the integral of it. That's why the local shear stress changes. And as a result, the local drag force, dFx, changes. And then we have to take the integral to find the total drag force. That's the concept of it. Now, here's a question. Keep in mind, we are discussing a smooth, flat plate. I'm not discussing a rough flat plate. For that case, there are experimental equations, and there is a graph that is like the equivalent of the Moody chart for flat plates, and that would be the next video. We're going to talk about that in the next video. For this one more time, if you're taking notes, we are just discussing a flow, a parallel flow over a smooth, flat plate. That's what we're discussing. Now, what's the solution for this? They apply the boundary condition to solve Navier-Stokes equations. They apply the boundary layer solution for it, and they come up with the solution for the laminar and turbulent local friction coefficients. So let's take a look at those values. All right, so I am showing you a page from the Chengel's Fluids Mechanics. It's a very famous book. A lot of students are using it. The guy has a book for thermodynamics and heat transfer, and they're very popular books. This is chapter 11 of that book. And so this is the local friction coefficient for laminar flow when it is smooth. And this is the turbulent local friction coefficient. So let's write that down in our notes and talk about the significance of these. So for laminar flow, smooth, flat plate. For laminar flow, when Reynolds X is less than 5 times 10 to the 5th, the equation for local friction coefficient is 664 over the square root of Reynolds X. I'm going to tell you something about this equation. This equation, in fact, is exact because for laminar flow, there is exact solution. It's exact and accurate at the same time. So this is the exact solution. For turbulent flow, when Reynolds number is less than this equation works in this range of Reynolds number, CFX is 0.59 over Reynolds X 1/5. This equation is an approximate equation, but accurate. But it is an approximate equation. You need to keep that in mind. This is not an exact solution because it comes from the power law, velocity profile for, the velocity profile over around a flat plate. So now, what does that mean? Let's take a look at that graph, that flat plate one more time. This is that flat plate. Somewhere in the process, you have the critical X. What does critical X mean? This is X equals 0, so X equals L. Critical X is where Reynolds X critical becomes 5 times 10 to the 5th, like that. And for this area, the equation you need to use for CFX is 0.664 over Reynolds number, the square root of Reynolds number. And for this area, I use a different color. After Reynolds critical, CFX is 0.059 over Reynolds number 0.2. 1/5 is 0.2, right? That's what it means. Now, if somebody tells you, I need to calculate the total drag force, then what are you going to do? You have to take an integral with different equations of CFX in the laminar area and in the turbulent area to be able to calculate it. So eventually, if you are looking to calculate the total drag force on this thing, you will have to do this. You will have to do something like this. The total drag force would be the integral of 0 to x critical. First, you have to take that integral from 0 to x critical of df laminar plus the integral from x critical to L dfd turbulent, like this. Because for every case, one more time, if I want to show the relationship between df dx is supposed to be CFX times dynamic pressure times dA. And of course, we know that dA for this case is W times dx, W being the width of this plate, like this. So that's what it means. That's what local friction coefficient means. This is so something that I have seen, a problem amongst the students that, they can't comprehend this. What does local friction coefficient mean? What's the significance of it? Well, how can I use that to calculate the total drag force? Luckily for you, already these integrals, have been taken, and they are in the book. And in the next video, we're going to talk about how to calculate the total drag force on a flat plate, and we're going to deal with at least 4 different categories. The categories are: what if we're in the laminar area? The plate is small enough; it's not long; it's like short enough that you fall into the laminar area, and then you calculate the drag force for laminar flow. What if the plate is actually long, just like this example I'm giving you, that at some point, the boundary layer goes from laminar to turbulent? Then you have to take 2 integrals to find the total drag force. What if somehow we tripped the boundary layer, or the surface was rough at the beginning, or something happened, like the flow of air over a circuit board when you want to cool down a circuit board? You have a circuit board, the circuit board could be like a smooth plate, but you have some capacitors and resistors and stuff like that that actually act like turbulators, and they trip the boundary layer, and the boundary layer becomes turbulent. Then, well, for that case, what am I going to do? What if the plate is actually rough? What am I going to do? What if Reynolds number is more than 10 to the 7th? What am I going to do? So these are like categories that we're going to show you in the next video. And of course, there are some videos that I'm going to solve problems with numbers, and we're going to identify this in what category this problem is going to fall into. And then we're going to solve the problem. So right now, we're going to stop here and look at the link in the description and look at the next video where I talk about the average friction coefficient and how to use it to find the total drag force on a flat plate external flow.